Okay, welcome everybody. So last time we went over non-deterministic finite automata, deterministic finite automata. We talked about the definitions of them, state diagrams, and all that. So today we'll continue down that path and we'll show how we can actually go from a regular expression and automatically generate a lexer. This means, unlike what you guys are doing for your lexer, where you're hand coding specific tokens for your compiler, you can actually write a regular expression compiler that takes a regular expression and automatically generates a lexer from it. And today we'll see the techniques and algorithms that allow you to do that. But before we do that, I want to just remind you that I updated the syllabus to have these readings from the Dragon book. I neglected to do this at the beginning of class, but I put them in now. I would recommend everybody at least read like chapter 1 and at least part of chapter 2. So chapter 2 is basically your programming project for the semester. So it might give you some tips on, it's an example of writing a lexer and a recursive descent parser for a different language, but you might be able to find some tips from that. So yeah, if you want to get more formal depth, if you want just more review of the material, so the Dragon book is way more formal, but it's also more comprehensive. So I'd recommend reading it if you can. These readings will follow closely what we talk about in class. Okay, questions from last time? Questions about the project? Yeah.
How many tokens would you have per expression? Like
how many
maximum amount of tokens you would have?
Tokens per expression or tokens per source
like
file?
3 plus 3 semicolon. That's like four tokens per expression.
Yeah.
Like I have mine set to 30. Is that enough, or should I have more than that?
Well, once we get, that would be okay for this project since each statement is a maximum of 5 tokens.
Oh, okay.
But once we get to the next project where we have arbitrarily large expressions, that won't work.
Okay.
That won't work very well. So you'd have to do dynamic, use a linked list or something.
Oh.
But the way we're going to handle it next time is we're going to use recursive descent. So all of the dynamic state will be in the call stack. So you won't actually have to buffer the entire print statement necessarily. But we'll see that when we get to the next project. But for this project, yeah, you can assume there's only going to be 5 tokens if you so choose. But remember, for the next project, that will change. Other questions? Yeah.
I imagine we don't have to deal with this, but let's say we're given a really weird output like print 1 to X. What would we do in that case?
Well, so as I said before, I'm not requiring you to do, I won't give you syntax errors because they're kind of annoying to deal with. There are ways to recover from them and have good error reporting. That's kind of its own engineering problem in real world compilers. But you can just fail. You can just fail. You can have undefined behavior if you want, where like you assume the input is correct and then you'll probably get some garbage output. Ideally, you should be recognizing the input. So when I went over that lexer skeleton last time, I was encouraging you to have a return value from the token that would allow the caller to determine whether the token was actually matched. So if you couldn't match a number, you can return null. If you couldn't match the print keyword, you can return false. And then your statement method or your main method can check whether you actually had a valid return value from those functions. So you can just error out. You can just exit and give an error message.
Exit. Okay.
Yeah, okay, so that was probably a 1-sentence answer that I gave 20 sentences for.
No,
Okay.
I don't mind the whole thing.
All right, other questions? Nothing else? Okay, so let's get to it. So this lecture is going to be a lot more formal. We're going to go over a pretty formal algorithm for doing this. It's probably somewhat similar to discrete 2 if you take that in the future or you're taking it now. But we won't do any proofs in this class. So just to review real quickly, why don't I also review lexing real quick? So just to quickly review regular expressions. So who remembers the 3 operations that you have? You must have minimum for regular expressions, yeah.
Closure.
Closure, good. Clean closure. So what does closure mean? 0 more times, that's good. What else? Are there any others? Yeah? Alternation, good. What does alternation mean? Must be one character from the language on the left operand or one character from the language on the right operand, but not both. And concatenation, the characters must follow each other. So the kind of formal definition of this is if we have some language, and so does anybody remember the definition of a language in this kind of formal setting? What's the definition of a language? Anyone remember? It's not on the slide. Well, regular expressions are one way to express a language, but not the only way. Yeah. Yeah, all the possible, exactly, yeah. So given some finite alphabet of symbols, a language is just all the possible utterances or all the possible sequences of symbols in that language, in that language. So that's all it is. It's just a set of strings. But these can be potentially infinite. So a C program, there's no bound on the size of the program, at least in the definition of the language. Maybe you'll run out of RAM for your giant program, but the definition of the language doesn't bound the size of the valid programs in that language. So the language itself can be an infinite set of strings. Regular expressions are one way to define a language that could potentially be infinite. So this is all about, if you think about English language or any human language, there's no real bound on the number of possible sentences you could say in English. Maybe there's a pragmatic bound to it. And the problem is, how do we kind of formally describe what a language is in some finite representation? And regular expressions are one way to define at least some kind of language. For us, it's for defining the lexemes of our language, the tokens of our language. But as we'll see once we get into a more rich language that has arithmetic expressions, regular expressions won't be enough for that. But regular expressions is one formal way to describe languages. And the languages that can be described by regular expressions are just called regular languages. And so the definition of a regular language is just a language that can be specified with regular expressions. That almost seems like kind of circular logic. But the interesting part about it is that these languages can be represented, regular languages can be represented one for one with finite automata. So the interesting part about that is that we have this model of computation, which seems like it's maybe not really related to languages or language processing, but it matches exactly this model of languages that linguists came up with, regular languages. And so what that means is that language and computation kind of are these like dual things. You can represent your language with this linguistic expression, and you can actually process that language using a model of computation, these finite automata. So before I go on, any questions on regular expressions? The last homework was for, I know it's not due till next week, but that was having you work with regular expressions. Does anybody have questions about these regular expressions before we move on? No? Okay. And if you remember the lexical specification file for your project uses regular expressions a little bit to define the identifiers and the numbers. Okay, so just a quick review of automata. Remember that automata, so can I get anyone to tell me what an automaton is? A finite automaton. Anybody? Yeah.
So it's like when you make an insert, it goes like that, and then after that.
So an input, like, what's an input? What are the inputs to an automaton?
So it's pretty much like when you put a coin, it gets unlocked. So an input is like what it's doing is it's giving a key to it. To do it.
Well, in the formal language sense, they call this a symbol. So there's just like in regular languages, there's a finite set of symbols, and the automaton can process these symbols one at a time and change its state depending on what symbols it sees. Change the state not only on what symbol it sees, but what state it was already in, and then how that symbol causes it to transition to a new state. So the example was, as you pointed out, you have this turnstile. It has we can abstract the kind of computational model of this turnstile and say it has two states, locked and unlocked, and depending on what input you give it or what symbol, if we want to turn this into formal languages, it will change its state according to how we define this formal automaton. So once you take discrete 2, they're going to go into like more of these models of computation all the way up to Turing machines, which are, as far as, this is like the most general computing model that we have. But this is sort of like a baby version of a Turing machine. It can do a smaller amount, it can compute a smaller amount of things, but as you get up to Turing machines, they kind of work in a similar way where they're like state, you can model them as state machines. And we can draw these state machines in a number of ways. One convenient way for us is using this state diagram. And the state diagram uses circles to represent the states. They can be labeled like 9. So this 9 has nothing to do with the language. It's just a label for the state. And transitions between states are done using arrows between states. So transition between states are these arrows that are drawn between states. So it's kind of like a directed graph. And the transition is labeled with the symbol that causes the state transition. So for instance, in our turnstile, the coin causes the state transition from locked to unlocked. So in this case, if we're trying to lex an identifier in our language, then seeing a letter will transition us to the next state in our language. The reason this models a regular language is because our regular expression says an identifier has to start with a letter, and then it can be any number of letters or digits. So this state machine models that exactly. We start seeing no symbols, we see a letter, and we move to this new state. This new state represents the fact that we've seen a single character already, we've seen a single letter already. And by having this recursive transition here, 10 just continues to transition to itself. By transitioning, whenever we see a letter or a digit, we capture the fact that there's this 0 or more letters or digits that can follow it. So each of these states kind of represents a position in the input or a position in the regular expression that we have been processing the input with. So start states are just this in arrow. Accepting states are represented with a double circle. So I want to stress that this is just a representation of a finite automaton. In the computer, and if we actually implement this in a computer, we probably wouldn't use. We can't draw on a computer, right? It's just we have to use an algorithm to describe it, and we'll get into that today a little more. So questions on this so far? Questions on state transition diagrams, finite state automata, regular expressions. Okay, you're all with me, or you're doing something else. Let's see if there's anything else. Oh, okay, so let's look at one other representation. So one thing, one other distinction is there are non-deterministic and deterministic finite automata. So who can tell me the difference or define one of them? Yeah.
You can change states when given the empty string.
Well, that's all automata. All automata will change states depending on the input string you give it.
The empty string.
Oh, empty string. I'm sorry. Given the empty string. So yeah, that's one attribute of which? Deterministic or non-deterministic? Non-deterministic. So why is that non-deterministic?
Because it could possibly be in two states.
Yeah, exactly. That's the key. So in this non-deterministic finite automaton here, epsilon represents the empty string in our languages. And because the empty string can always be recognized, in order to try to follow the state transitions of this state diagram, we have to effectively be in both states at the same time in order to recognize all possible inputs in the language. Yeah?
One thing that I was talking with another student last class about this, so
Yeah.
it was, say, I have an if statement, and inside of that block are two if statements.
Uh-huh.
So in that case, when we go into that first if statement, we would be in a non-deterministic scenario because we have two other conditions we might go into at that point.
Yeah, that's true. Yeah, you could you can certainly represent this using code, which is exactly what you're doing in your compiler. You're turning this into if statements and while loops.
So it's like I'm just want to make sure I understand this. So when we're in a situation where it's non-deterministic, could we just basically say?
I see.
Could we basically say that that's a situation where there are several possibilities that might happen, and we don't know yet which one.
You can represent it like that, but strictly speaking, in your program, you can think of the program state as being your instruction pointer, like where in the program you are. So in that sense, programs are only at one point, sequential programs at least. Not talking about parallel programs, but sequential programs are at a single point in the program. So when, in that scenario you said where you have a nested if statement, when you enter the first if statement, you're as if you're here. You have to make a deterministic choice about which next statement in your program that you want to process. So what I'm going to show today is that you can always convert a non-deterministic automaton into a deterministic one. So strictly speaking, if you want to convert a state transition diagram to code, that code, and as long as it's sequential code, you're not doing parallel processing, that code is deterministic. So strictly speaking, this wouldn't be modeled in that situation. I think what's happening is that you can take this program and you can turn it into a deterministic finite automaton by basically like eliminating these epsilons and having a single starting state where you're deciding whether between A or B, whether you're seeing A and B. So what I'm trying to say here is that if we remove these epsilon transitions and just have a transition from 0 to 2 on A or 0 to 4 on B, we can just readily turn this into a deterministic automaton, which is effectively what you're doing when you're writing a program. Yeah.
Is it possible for an NFA to have one final state?
Yeah, for sure. Yeah, you can have 0 or more final states. It's possible for a DFA to have more than one final state also. Because there's no limit on the number of final states. But it doesn't mean you're in those states at the same time. But in NFA, you can be in multiple accepting states at the same time also. But that's possible. Yeah, I mean, it's possible. It means there's redundancy in your NFA. So another point, I mean, this is probably more for discrete too, but there are, for a single regular language, for a single set of strings, there are potentially many automata that recognize that language. It's actually probably infinite for NFAs because you can always arbitrarily add epsilon transitions and have just any number of different NFAs. And there's actually provably a minimal deterministic finite automaton for any regular language. But take discrete too, and they'll go through proofs with that. Okay, so just final review is that instead of just state diagrams, if we want to represent it more conveniently, say in a computer program, we can represent all of these finite automata using transition tables. The way a transition table works is each row, at least in this case, represents one of the states. Each column is a symbol. And in order to figure out the transitions between states, typically the first row is the starting state. In order to determine transitions, we just look at what state we're in. We look at the symbol that we see in the input, and that tells us what next state to go to. So if we're in state 0 and we see B, that means we stay in state 0. If we see A, because this is non-deterministic, we go into 2 different states at the same time. So we're in both state 0 and state 1 until we see the next input. So if it's a B, then we have to enter 2 and enter 0 again, and so on. So questions about the transition table representation? Yeah.
I'm sorry, you said for state 1, if we are in B or 2, then we go back to 0?
I'm sorry, don't go back to 0. I sort of rushed through that a little bit. But if you're in state 0 and you see you see A, you're in both 0 and 1. So if you end up seeing a B, you have to do both transitions, both from 0 and from 1. That's why you'd end up in state 0 and state 2. It's probably more easily seen here. Or if you're in state 0 and you see B, you go to, oh wait, I'm getting confusing myself. What did I say? Oh yeah, sorry. You're in state 0 and you see an A, so you have to both be in 0 and A. I'm sorry, 0 and 1. So if we then see a B, we're in both 0 again and in state 2. Does that make sense? So this is for, homework is sort of working through one of these, one or two of these automata. Okay. So today we're going to show how we can go from a regular expression to an automaton. So the automaton can be pretty easily written in code. You just once you have that transition table, the algorithm for doing it is pretty simple. You can read that in the Dragon book. You just have a variable that says what state I'm in, and then when you get a new symbol in the input, you read one character at a time. You look up in that table, what state am I in? What symbol did I see? And then you just go to the next state. That's way easier, as you might be able to imagine, if you have a deterministic finite automaton, because there's only one state you have to track. If it's a non-deterministic one, then you have to track many, many states. And so there are two ways that we can do this transformation. One is simulating the non-deterministic finite automaton, and that means we have to actually just, instead of having a single variable representing a state, we have to have a list or an array representing all the states that we're in at the same time. Or what I'm going to show you today is we can convert from a non-deterministic finite automaton to a deterministic one. And we can do that using an algorithm, an automated algorithm that can be implemented in code. So this algorithm is called the subset construction algorithm. And remember, non-deterministic finite automaton can be in multiple states at the same time. But notice that in the definition of these automata, there are a finite number of states. So therefore, what does that mean? If you have 5 states, there's a finite number of multiple states you can be in at the same time. There's a finite number of subsets of those states. So even though the non-deterministic finite automaton can be in multiple states at the same time, we can actually count all possible combinations of these states. That's also finite. And so a little maybe math question for you is, if I have some number of states, some number n or 10, how many subsets of those states are there? So this is a set theory question. 2 to the n? Good, yeah, 2 to the n. The power set. This is the power set. So that's all the possible multiple states we could be in with the non-deterministic finite automata. And the key to the subset construction algorithm is that we can turn all of those subsets into single states in a deterministic finite automaton. And I'll show how that works in a second. But first, we need to convert the regular expression into the non-deterministic finite automaton. The way this works is we take each sub-expression of that regular expression and we convert that sub-expression into a non-deterministic finite automaton. I'm going to say NFA from now on. This is very long to say. We take each sub-expression of that regular expression, convert that into an NFA, and then we can gradually build up a bigger and bigger NFA. And each of these regular expression operations corresponds to a very simple NFA template that we can then just start gluing together. So let's start and try doing this a little bit intuitively. Let's see if we can kind of intuit what these NFAs look like for each of our regular expressions. So if I've got, this will write. Oh, that's not good. Sorry, technical difficulties. Uh-oh, this is not writing. Oh well. Okay, so if I've got just concatenation, how do we represent that with an NFA? Any takers? Yeah.
The epsilon transitions to, no, wait, never mind.
Okay, yeah.
You have an epsilon transition from A's final states to B's start states.
Well, what is A? So there is no A state. State is a symbol that's read from the input that causes state transition. So let's assume we have a starting state here. Yeah.
So from that starting point, so we have a transition due to A that goes into some new state.
Okay.
And then from there, we have a transition using B that goes into a third state.
Yeah. That sounds right. So just to, let's see if we can, oh, I can't use my laser pointer. Oh well. So if we have, yeah, so if we're starting in this state, we haven't seen any input yet. We see an A, so we transition to this state. If we see anything other than a B, it's an error. We can't transition to the final state. And then if we see a B from this middle state, that causes us to transition into our final state. Questions on this so far? Questions on this? So no matter what these, even if we don't have A and B, even if we have some complex regular expression instead of A, the kind of pattern of this DFA is that we start on some starting state, and somewhere in here we've got some complex sub-expression that eventually leads us to some middle state, and that middle state also reads some complex sub-expression and reaches the final state. So it's just kind of a template for doing concatenation. So that's an easy one. What about alternation? What if we have A or B? How can we draw that? So there's many ways to do alternation for sure, but how can we do that with a non-deterministic finite automaton? So let's assume we have our starting state, and let's have our ending state as well. Let's give it a single ending state. Any takers? Yeah.
2 arrows
Two arrows pointing
pointing to the accepted state.
to the accepting state. So
And then, each one has their own letters, so A on top of B.
like this and like this. Certainly, you can do it that way. Let me give you a slightly harder one. Well, actually, is there any other way we can write this? Like, if say we had A, C, or B, D. We have our starting state. Yeah. Yeah, that's right. That's right. So you could just do the same deterministic construction. So I'm going to give you another way to do this that will actually end up being easier to use. But I realize this is not like obvious why you would do this. So instead, I'm going to do it like this, where from my starting state and to my final state, I'm going to use epsilon transitions to split into two sub-expressions. So whatever I put here will be very easy to join together. Now I'll do an example of this to show why this is fairly straightforward. So for the last example, let's say I've got, well, yeah, this is going to be like way too easy. So let me see if I can make it complicated. Let's say I've given you, for this sub-expression, I've given you the regular expression. How would we turn that into clean closure? Loop back, well, there's no states here. So let's say that I've got a state here that will enter my complicated sub-expression, and I've got a state on the outside that will leave that complicated sub-expression. I haven't written the entry state or the final state yet. But let's say I have the situation where I've given you the automaton for this very complicated regular expression, and all you have to do is make the clean closure of that complicated regular expression. Yes, go ahead.
Could you point the could you have an arrow coming from the accept state to a new start state and have that negative transition?
So like this?
To a different one and have that like epsilon transition.
Oh, I'm sorry. Can you say again? So I'll number these as 2 and 3.
Would you create a new one?
A new one.
And then have that epsilon transition into 2.
Epsilon transition into 2.
And have
3 transition into 1. So 3 transitions into epsilon transition, right? Okay. So let's try to use this. So let's say I'm in state 1. What happens? I'm in state 1, and then I immediately transition to state 2 and immediately transition into my regular expression. So there's one little wrinkle here. What does clean star mean? Clean star means 0 or more. So if I'm here, I have to at least recognize one regular expression, or recognize this regular expression at least once. So this is close, but how can I solve that? You can go straight from 2 to 3. Ooh, why is this not working? Okay, now this isn't working. Hey, the pen works now. That's odd. So I can go straight from 2 to 3. So will this work? So what happens when I do this? If I'm in state 1, I immediately transition to state 2 and to whatever state this is, but I also simultaneously transition to 3. So I'm now in state 3 and at the beginning of my sub-expression. So now I can either continue on past state 3 to my final state, 4, or I can read one of my sub-expression, or I can read the sub-expression. Once I finish that sub-expression and I'm in state 3, I can either immediately go to the final accepting state, and I'll go back to the beginning state and repeat the process again. Yeah, go ahead. Question?
Would it not be an issue that when you go from 2 to 3, you'd also go back to 1, then back to 2, and then back to 3 again?
Well, no, it wouldn't be an issue because we are only in one state at one time. So we can't be in state 2 multiple times. We're either in state 2 or we're not in state 2. So if we're in state 1, we would end up also being in state 2, also being in state 3. And the fact that there's an epsilon transition back to state 1, I mean, yeah, if you wrote your code poorly that simulates this, you may just like have an infinite loop. But in the model of computation, you're only in a state or you're not in a state. So you can't be in a state multiple times. But yeah, interesting question. Yeah.
What makes epsilon, like using epsilon transitions easier than just regular transitions?
To see, well, ask that question in a little bit when I go over generating an NFA, and I can go over an example that will show that it's kind of harder to make a DFA directly from a regular expression because of the alternation. But I think I can show an example of that. Your homework may also be an example of that. But ask in a little bit after we do the NFA, and we can try to construct the DFA for the same example. Okay, questions on this so far? Yeah.
Would it be a problem if 3 was an accept state?
If 3 was an accept state? Would it be a problem? It wouldn't be a problem for this example, but once we start gluing these together, it would be a problem because you would maybe have you might have some regular expression after here. You might have some regular expression here that you want to continue on reading. So you have to read that in order to accept your input string. Yeah.
Solution accurate, or
What? Say again?
what we came up with, is that?
Well, let's take a look. So here's the Dragon Book's little templates for doing these NFAs. And so concatenation is exactly what you guys said. So you have your initial state and your final state, And whatever regular subexpression you have, some NFA for a subexpression, you just glue the final state of the first subexpression to the initial state of the second subexpression. And that's it. That's concatenation. For alternation, so it was a little harder for me to motivate this because like why would you like add these superfluous epsilon transitions? But once you do your homework, I think tonight's homework, for next week, you'll probably find that it's easier to just kind of do this mechanically, where you use this template rather than trying to figure out what transitions we should make from the initial state. Because the transition, if we didn't use these epsilon transitions, we'd have to incorporate the beginning of NS and NT into our transitions from the initial state. It would depend on whatever the subexpressions are. So if this first one is itself an alternation, you would end up with many exit branches from here. And if these two subexpressions happen to use the same inputs, then we'd have to make, it'd still be non-deterministic. We still have non-deterministic choices. So that's alternation, and clean closure is a little bit more complicated, pretty close to what we did. You take the initial and final state from your subexpression, and you use that back edge to account for the repetition. And then to account for 0 or more, you create extra states for the initial and final states. That's why you kind of have this extra 2 states here in the clean closure, because this edge, as your classmates correctly pointed out, accounts for the 0 repetitions case. If this were, instead of clean closure, it was the the additive closure, where it was regular expression plus 1 or more, then you wouldn't have this. You wouldn't have this edge. Questions so far on this? Is this fun? A little bit. Okay, so let's build the NFA for this regular expression here, and I will try to keep these templates visible. I don't think template is the actual word for these, by the way. I don't know what the real word is. Oh, get out of here. Okay, so let's look at A or B star, A, B, B. Now, if you read the Dragon book, the way they do this is they actually, this is what's confusing about compilers, is that to write a compiler, you have to use a language to express the compilation. So there's always this confusion between the source language, the language you're writing the compiler in, and the target language. It's the same thing with regular expression compilation when you're compiling it to an automaton. In the Dragon book, they treat this regular expression itself as a language that has its own grammar and syntax. And so they will draw a syntax tree for this regular expression. And then you traverse the tree. We'll learn this when we learn about parsing, but you traverse the tree, and starting with the leaves, you process each node of that tree, each operation in that tree from the bottom up. But I'm just kind of do it a little bit more intuitively here, since we haven't really gone into parsing yet, and just say that the order that we process these subexpressions is in the order of operations order. So the parentheses, just like in math, they enforce, they make explicit order of operations. So in this regular expression, what is the first operation? If this were a math expression, alternation would be like plus, concatenation would be like multiplication, and clean star would be like exponentiation. It has the same order of operations. So in this expression, what is the first subexpression that gets computed? Alternation, yeah, good. The alternation. So we take our we take our alternation pattern, and we use that. But what are the subexpressions of alternation that we have to compute? The A and the B, yeah, they're just individual They're not even like individual sub-expressions. So to recognize just an individual letter, I didn't really say this explicitly, but to recognize an individual letter, it's just one initial state, one final state, and you just transition on that letter. So it's almost it's kind of trivial, but I should probably mention that this is the automaton for just recognizing a single character. Okay, so we have two possible sub-expressions of the alternation operator. Those sub-expressions happen to be just a single symbol each. So then we can use our alternation pattern here to implement alternation as an NFA. With me so far? Questions on this so far? Yeah.
Why do we have two states for each character?
Two states for each character? Because a character, so in order to recognize a single character, well, first of all, that's a good question. Why two states? You could, if you're trying to recognize a single character, you could, well, yeah, you would have to have a minimum of two states to recognize a single character. Because when you are at the starting state, you've consumed no characters, and you need to have a second state to represent the fact that you've seen at least one character. So recognize a single character requires a minimum of two states to do that. So we're in a starting state here. We've seen nothing. And when we have a transition that takes A and transitions to another state to record the fact that we've seen a single character in the input. So, okay, yeah, so this is why we have two states to recognize a single character. So the states, so it might be confusing here too. It might be easy to confuse the states with the symbols themselves, but the states are more like where you are in the process of recognizing the input. And the input is what causes transitions between states. So the states themselves are not the symbols of the language, but in a sense they represent like partial prefixes of the language. It's one way to look at it. Maybe that's too formal for it. But yeah, if you want to recognize a single character, you need two states to do it. Other questions on this? Other questions? Everyone with me? I think you're all with me. Okay, so what is the next operation that happens in this graph, in this automaton? Sorry. Clean closure. Good. Yeah. So it parenthesizes the alternation. So that's the next thing that we need to do. So the reason that we have these nice templates and all these seemingly unnecessary epsilon transitions is that they make it really easy to compose these sub-expressions. So now I can just treat this entire diagram here as just a sub-expression. I don't care what it is. It has an initial state, it has a final state, and I just ignore what's inside and I just use my clean closure template in order to implement the clean closure sub-expression. So I add my initial state for the clean closure and my final state for the clean closure. And then I've got the epsilon transition immediately to the final state, and which accounts for 0, and my epsilon transition to between the sub-expressions final and initial states, which accounts for the or more part. So this is 0, this is or more. Questions so far on this? Any questions on this? Yeah.
Is there a difference between a clean closure and just closure?
The term, I think, well, closure in math has a much broader term. Like closure is anytime you have two operations and the result is in the same set, I think, as the initial. Does anybody here do math and know the definition of this? Okay, so I can fake my way through it. So closure is like anytime you do the same operations and you do an operation on two things from a set and then the result ends up in the set. Clean closure is like something specific to these regular languages. But closure itself is sort of a broader term, like transitive closure. Closure is used a lot in math.
Yeah, so I mean, on the other slide, way back there, I think one of them just said closure.
You said closure, yeah. So I'm just being a little sloppy with terminology. So based on the context of being in regular expressions and regular languages, in that context, closure has the meaning of clean closure. So yeah, sorry for the kind of abuse of terminology. Closure is we're actually going to see another use of the word closure in a second. Okay, other questions on this? Questions? Okay, this is great. I think you're all getting it, or not paying attention. Okay, so what's the next operation? Concatenation. Concatenation of this A after the clean closure. So how do we do concatenation? Yeah, we just glue them together. So we have our so to be kind of pedantic here, this is our NS here, and then our NT, that's the recognition of A. So this is the initial state of NS, and this is the middle state. So we just take the final state from the first subexpression and turn it into the initial state of the second subexpression. When we're concatenating just a single symbol, it's kind of intuitive. You just like draw the arrow. But if you had a more complicated expression here, like another alternation with a clean star, yeah, you'd want to just be very careful to make sure you're joining the final state of one subexpression to the initial state of the other subexpression. So here it's like kind of almost like intuitively you can write this, but just be aware of that. So yeah, so then we just take our transition on A and join the initial state for transition on A to the final state of our larger expression, and then it's just easy from here. There's just two more. So I ran out of space, unfortunately, but there's just two more transitions for B, and we can have our final state finally. So I rushed through that ending a little bit, but any questions on that? Yeah.
So if, instead of that first A, you have like an alternation there following that.
Yeah.
You just go right into where, like, if you're going into that epsilon at the beginning, so to speak. Right into the alternation.
Well, let me do an example of it. Let's say we had. Let's just do an example. I think that might be clear. It'll show concatenation a little better. So let's say we had. Let's do A or B, followed by B or A. That's kind of lame. Let's do C or D. So let's go through this. Let's just go through this real quickly. So alternation would be, we use our epsilon transitions to go to the two subexpressions, and our epsilon transitions to go to the final state of our alternation. So then if we have, I'll just sort of, I'm going to make the C or D kind of separate here. So if there's some start state, we again do the two epsilon transitions, and they just recognize C or D, and then epsilon transitions to their final states. So this is the initial state of the A or B subexpression. This is the final state of the A or B subexpression. This is the initial state of the C or D subexpression. This is the final state of the C or D subexpression. So the way this pattern works is we take the final state of the first subexpression and make it the same as the initial state of the second subexpression. You could certainly also do a pattern where you use an epsilon transition, if that just sort of makes more sense to you. Like we could have drawn this pattern like this, where this is our one subexpression, and we could have just done an epsilon transition between the two subexpressions. That, I think, is just equally valid to do. You can certainly do that if that makes more sense. Or, like in the first case, we can make the final states and the initial states the exact same state. So in this case, it would be like a very awkward large state in the middle here. Make sense? Questions on this? Yeah.
So that rightmost F, could that be your accepting state?
That could be your accepting state. Yeah. So it's whatever is the last sub-expression that you have, or you can have an epsilon transition to an accepting state. You can do that as well. So even though a non-deterministic finite automaton might be a little like harder to wrap your head around, they're actually easier to use to automatically construct automata from regular expressions. Questions so far? Questions? Okay, let's see what's next. Oh yeah, we have the. Okay, so those are the patterns. This is the exact same automaton that we just constructed. That's also from the Dragon book. They go through it in more detail in this construction. Okay, so now that we have figured out how we can take a regular expression and turn it to an automaton, how do we actually run that on a computer? How can we take this automaton and actually run it? So I hinted at the two different ways that we can do this. So one is the subset construction algorithm. So remember that an NFA can be in multiple states at the same time, and we can take sets of these multiple states and just call them a single state in a deterministic finite automaton. We can also simulate being in multiple states at the same time. So if you have your transition table and it tells you to go to multiple states, you just have an array or a linked list that keeps track of all the possible states you're in at the same time. So I'm going to do the subset construction. The simulation algorithm is also in the Dragon books. If you look at it, if you take a look at it if you're interested. But I'm going to go through the subset construction algorithm. So this is just kind of a sketch of what this algorithm looks like. The way it works is we start at the starting state of the NFA. So you can, the like formal definition of these automata is that they have a single initial state. If you happen to have alternation at the beginning, you'll just have a bunch of epsilon transitions, but you can always have a single initial state. So this is assuming that there's one single starting state for the NFA. And then the first thing we do is we group together all the states that are reachable by epsilon, by empty string. So this is called the epsilon closure, but this is not the same closure as clean closure. This is the epsilon closure. It just means all the states that are reachable by epsilon transitions from a given state. Makes sense, right? We saw that example where we started at an initial state with alternation. We immediately had epsilon transitions into two other states. So we group together all these states that can be reachable by an epsilon transition, and we just take that subset of states and we just call that a single state in our DFA. We just make up a new state and just call it a single state in our DFA. And we say that represents this initial state, this set of initial states from the NFA. With me so far? Yeah.
So for example, with that case of where we just had that cloud and so we're putting epsilon in, that's the closure, safe to say?
No, not necessarily. The cloud is just represented as sub-expression. The epsilon closure, for instance, let's do an example. So if this is my initial state, what states are in the epsilon closure of this state? So this is my initial state. What states are contained in the epsilon closure? And these are not numbered, which makes it annoying. So let me number them real quick. 1, 2, 3, 4. This is supposed to be 5, 6, 7, 8, 9. Okay, which states are part of the epsilon closure of our initial state? Someone, raise your hand. Okay, yeah. 1, 2, 3, and 5. Any else? Yeah. And 8. So there's also this sneaky epsilon transition here. That's the epsilon transition. So what about 4? What is the epsilon closure of 4? Yeah.
4 and 7.
4 and 4, 7, 8. Anything else? 2, 3, 5.
Okay, so if they're all connected like that.
If they're all connected by epsilon transitions, it's almost like graph reachability,
Yeah,
if you learned about that. So yeah, go ahead. So 4, 7, 8, 2, 3, 5. Is that it?
Okay.
That's everything.
It's up until they're blocked by an
Yeah, up until you have to read in an input in order to transition on a state. So that's epsilon closure. Oops. Okay, so all right, so once we have an epsilon closure of our initial state, so that represents some subset of states of the NFA. That subset of states, we can just represent that using a single state in the DFA. So that representing a subset of states using a single state in the DFA, that's the kind of crux of this algorithm. And because we know that there's a finite number of these subsets, we can construct a DFA. It may have many more states than the NFA, but we can at least construct a finite one. Okay, so once we have that initial state, we go through each symbol in the alphabet, all of them. We just run through all these symbols in the alphabet, and starting in some state, initially that initial set of states, I'm sorry, not in a single state, starting in that initial epsilon closure of states, we find every possible state that we can transition to from that symbol. So remember, in NFAs, we can have multiple transitions for the same symbol. So we take all the states that can be transitioned from that. Once we do that, we take the epsilon closure of those states. So that gives us one transition from one symbol. It gives us all the possible states we can reach from the initial state through a single character from the input. And we have to do the epsilon closure again because we can have all these epsilon transitions that can all the states that you can be in. So you can quickly see that how this is like, for a human to do, this is like pretty tedious to sit down and do. But a computer can implement this algorithm like really, really easily. It can do it, it doesn't get bored doing it. And then you go through every symbol in the alphabet, and now you've got a bunch of, you record all of the sets of states that transition to other sets of states, and then we just take all the new states that we looked at, and we just do this again. We look at every symbol in the alphabet and see all the possible next states we can reach from that. And you just do this over and over and over until you've touched all of your states and symbols. So it's a pretty tedious algorithm to work through, but it's kind of cool the way it works and the way you can actually implement it in an algorithm to do this. Okay, so it is kind of tedious to do, but I'm going to do it. So let's take our example that we just worked with, and let me get a new note. This is no, I can use this. Okay, I'm going to draw this out again. Actually, for the sake of time, maybe I'll do a smaller. I'm going to do a smaller example because this, as I said, this is pretty tedious to do by hand. So you'll have to do it once for homework by hand, but it's not so bad. I say that. I have to do it every semester. So let's do this regular expression. So let me just write down the automaton for this. Let me know if I make a mistake. Let's just make that our initial one. And we need our Is that right?
We should have the return up after the second beat.
Yeah, after B, right?
Yep, you're absolutely right. Thank you. Is this right? Yeah, that's probably shouldn't have rushed this. So that's our sub-expression for the closure. And this is our, I keep changing the marker here. Nope. How's that? Is that right?
Yeah.
Okay, thanks. These are epsilons. I should probably number these to make it easier. Okay, so there's our DFA, or NFA. And now what we want to do is we start constructing our table, our transition table, so that we can record all of these sets of states that we're going to end up with. Give myself some space here. Okay, so let's start at our initial state, which I did not mark, which is here. All right, so we start at the initial state. We know it's going to be some subset. We start with 1. And what is the epsilon closure of state 1? 1, 9, 2, 3, 4. And that's it?
Yeah.
For that one, yeah.
You sure? Okay. Okay. So this is a subset of states of our NFA, and we can just turn this into one of these states of our DFA. So this is our NFA subsets, and we can call it a new state in our DFA. I'll just call it A in our new state, so I'm not confusing myself with the numbers. Okay, so now that we have one of these new states in our DFA, we can compute all of the possible transitions from this state. So starting with A, what are all the possible transitions from all of these states, 1, 9, blah, 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 blah. What are all the possible transition states for that? 6. So A, so where do we get state 6? 5. So we can do 5 because from state 3, A transitions to state 5. What else? So what about state 1? If we try to transition with A, what happens? There's no valid transition. State 2, no valid transition. State 4, no valid transition. So the only way that we can have a transition here is from state 5.
Yeah.
Is that right? Oops. Okay, now that we have the set of states that we can reach by transitioning on symbol A, what is the epsilon closure of state 5? So 7, just 7, right?
Yeah, because you hit the beat.
Just 7. So now I'm going to record this new subset under my set of subsets under this column and give it a label in our DFA. All right, so now we got to go through every subset and every symbol. So let's go to B from DFA state A. So what do we transition to when we are in our DFA state A? So from which one was it? From state 4, we can go to state 6. Anywhere else? 7. So where can the epsilon closure? Yeah, sure. So what about transitions for B? Transitions on B. Any other transitions on B? But nothing else, right? So then we do the epsilon closure. So epsilon closure, as everyone already said, is it can transition to state 7. Anything else? All right, so we've created a new state. What's that? 9?
No, wait, no.
Did I miss 9?
No.
Okay. All right, so we've got yet another state for our DFA, another unique combination of, so I mean, one way to look at this is these are unique combinations of states, unique subsets of states. That'll become relevant when we move on. Okay, so now we've got 2 new states and we don't know their transitions yet. We've got state B or 5-7. How can we transition using A from 5-7?
We can't.
We can't. There's no possible transitions. So we can just call this the empty state, empty set. What about for B?
We could go to 8.
So we can go to 8 on the transition. So 5 can't go anywhere from the state 5 cannot go anywhere with symbol B. It can go somewhere with epsilon, but the out edges of 5 there is no B. The only place there is an out edge is on 7, and 7 can go to 8. Okay, so then we do the epsilon transition of 8, or the epsilon closure of 8, and what do we get? We get a lot of stuff. So we get 9, 2, that's 3. Okay, you're going faster than this laptop. 2, 3, 4. Anything else? Did I miss anything?
I don't think so.
Okay. Making progress, except now we've increased our work here because we have a new subset of states. Oh, yes, more to do. All right. One thing to point out, which will be important later, this is an accepting state. So any subset that contains at least one accepting state itself is an accepting state. So that means A is an accepting state. I'll put a little double circle here. This is an accepting state. D is an accepting state. Okay, so now we got a couple more sets to go and 5 more minutes. So 6 and 7. Let's go quickly. So 6 and 7, how can we transition with A?
Can't.
We can't. How can we transition with B?
Same as the last one.
Same as the last one. Yeah, good observation. So notice that we're in state 7 when we're, where's this pointer here? So notice here, this is the state that we're working with, the subset of states we're working with. When we see 6 and 7, 6 can't go anywhere, but 7 can transition on B. And that's exactly how we transitioned from state 5-7. So it actually ended up in the exact same state, the same transition state and the same epsilon closure. Questions on that? Was that clear? So we've already found, we've reached a subset that we've already encountered before. So we don't have to do the transitions anymore. We know the transitions already, or we're about to do the transitions for that, which is our next state to look at. All right, so transitioning from A. Say again? I didn't write them the same? Oh, you mean because I have terrible handwriting? Yeah, I know. Okay, so what about transitioning from state DFA state D on symbol A?
5-7.
Okay, we have can't and we have 5-7. So which is it? So from state A, we can't. State 9, we can't. State 2, so I'm going to use a laser pointer. State 8, we can't. State 9, we can't. State 2, we can't. State 3, we can. We can transition to 5. And we have the epsilon closure of 5. So we get to 5-7 again. So this is why, doing this as a human is pretty tedious, but a computer can just systematically go through each one and check what's the transition for that. Okay, so we got 5-7, great. We have a state we've already seen. What about for B? So we have 6-7. Let's just double check that. 8, we can't do anything. 9, we can't do anything. 2, we can't. 3, we can't. 4, we can't. Or 4, we can, and go to 6. All right. Is that all the states? Did I miss any? It's everything, right? Yeah. Did I miss something?
So what, in the first statement, so when we were looking at A, where did you get
Why do we have 7 here?
No,
Here? Sorry. So that was the epsilon closure. I sort of rushed past that a little bit. When we're in DFA state D, that means we're in all of these NFA states, 8, 9, 2, 3, 4. If we want to transition using A, then we just go through each state one at a time. So we're in state A, nothing can transition from A, nothing can transition from A, nothing transitions from A. But when we're in state 3, we can have a transition to state 5. Once we find those transitions, we do the epsilon closure, which gives us state 7. Yeah, question?
Let's say that the transition from 4 to 6 was A as well. How would we rewrite that in the chart? So it's like.
I don't know.
So,
It would. It would be. Well, it would be different because basically the sets from B and the sets from A would be merged because there's only one. They're the same symbol.
okay.
So you would union these sets
we
probably.
We wouldn't have 2 separate blocks under A. We'd have one block that combines 5, 6, and 7.
Yeah, because there's only one symbol. There's only one symbol A that transitions. So there's one column per symbol. So just to bring this home in the last 30 seconds, we can. So this is state B. This is state B. This is state C. This is state C. And this is state D, right? So we can actually construct the DFA using this table as a diagram. So when we're in state A, when we see symbol A, we go to state B. When we see symbol B, we go to state C. When we're in state B, we can only go to state D. When we're in state C, we can only go to state B. When we're in state D, if we see an A, we go back to state B. And when we see B, we go back to state C. And D is our accepting state. Actually, I drew D twice, which is totally wrong, but you get the idea. I made it. Yeah, I messed it up. But anyway, it's 8:45, so let's finish up. All right, so yeah, we just saw how to go from regular expressions to NFAs, then NFAs to DFAs. Doing this once will be your homework. It shouldn't be too complicated, but yeah, now we have a deterministic automaton that was easy to implement in code.